Dear colleagues, as we unfortunately had to cancel this year's World Congress in Montreal, we thought it would be a good idea to at least share some highlights from the virtual Congress that took place in February. Before the video starts, I would like to announce that the 2022 World Congress in Taipei, Taiwan will take place from June 9th to the 12th. I look forward to seeing you there in person, and now please enjoy the video. Oh, and don't forget to subscribe to our YouTube channel below for free so you can watch more videos in the next weeks. Thank you.
Hi, my name is Hiroki Ueda. Please call me Hiro. Today I'm going to talk about phosphorylation hypersleep. So one of the biggest challenges in this field is to understand the sleep homeostasis. For example, if you cannot sleep well or in the night, next day you feel very sleepy. This is because within your brain there are molecular or cellular mechanisms to memorize neural activity over the time and then convert them into the sleepiness information. What is interesting here is timescale differences. Neural activity is usually millisecond to second, or on the other hand, sleepiness may last hours. So to test this hypothesis, we try to knock out the member of these four families. And then, unfortunately, this turned out to be 29 genes. So therefore, we face a challenge to knock out these 29 genes. So if you want to use a conventional method, it takes 1 to 2 years per person per genes. So therefore, we try to develop new next generation genetics, which is defined as a genetics without crossing. So we somehow develop this technology to make a knockout mice and knock-in mice within 3 to 4 months by using triple CRISPR or modernized ES-based technologies. So after we generate these knockout mice, we also face phenotyping problems. So conventional method like EEG-EMG recording is labor intensive and also very, dependent on the person to persons. So therefore we decided to develop non-invasive way to measure through sleep and wake cycles by using respirations. So we made a chamber respiration chamber by ourselves, and then we made a rack by ourselves, and then we made because CAM kinase 2 are activated by calcium and then store such information as autophosphorylation and then eventually convert such information into the kinase activity. Encoding mechanism, sleep information storing mechanism, and decoding mechanism are suggested. So to validate this hypothesis, we try to look at the autophosphorylation status and outcome of the autophosphorylations. CAM kinase 2 alpha beta has 54 possible phosphorylation site and 69 possible phosphorylation site. We first focus on the CAM kinase 2 beta and then try to overexpress phosphomimic mutation one by one in adult mice. Here is an animal-based screening of possible phosphorylation, and then we are lucky enough to identify some autophosphorylation mimicking mutant significantly increase sleep, which is high contrast with the phenotype of the wild type overexpression. And also, we try to test the decoding mechanism by creating artificially kinase active mutation of the mutant of the CAM kinase 2 beta by deleting C-terminus of the CAM kinase 2 beta. Overexpressing these artificially kinase active mutation increase significantly sleep length, and also these effects are cancelled by kinase dead mutations. So based on that, we propose calcium signaling seems to be determining sleep and wake status, and CAM kinase 2, which is downstream of the calcium, may store the sleepiness information as autophosphorylation status. And then we call these hypotheses as phosphorylation hypothesis. Let me switch gear from non-REM sleep to REM sleep, which is another important sleep of the brain. So, cellular circuit of REM sleep is well investigated, but not so many work has been done for molecular identity of molecular circuit of the REM sleep. So, whenever single M1 knockout or single M3 knockout does not exhibit the original phenotype, which is twice larger phenotype than M1 alone or M3 alone knockout mice. So therefore, we try to generate M1 and M3 double knockout mice by using triple CRISPR. And then we found a very strong sleepless phenotype in the double knockout mice. So therefore, we try to analyze EEG-EMG phenotype to dissect non-REM sleep and REM sleep in M1 single knockout mice, M3 single knockout mice, and also M1, M3 double knockout mice. And then interestingly, M3 receptor exhibited reduction of sleep, and we also observed non-REM sleep reductions. REM sleep is not affected as a total duration, but we also see some fragmentation of REM sleep. So, indicating M3 receptor seems to be important for non-REM sleep. So, in summary, in non-REM sleep, calcium and also calcium downstream kinase called CAM kinase 2 has a role in determining and also memorizing of sleep and sleepless phenotype informations. In REM sleep, M1 and M3, which are both of them are acetylcholine receptor, have a role in REM sleep as essential genes.
Well, hello, everybody. My name's Andrew Tobin from the University of Glasgow, and it's a great pleasure to be talking to you, and thank you, the organisers, for giving me this opportunity. I'm going to tell you one thing that you know and a few things that you don't know to orientate ourselves for this talk. You'll know that in Alzheimer's disease, there is a deficit in cholinergic signaling, cholinergic innervation to memory centres such as the hippocampus. And cholinergic signaling focused around acetylcholine is terminated by acetylcholinesterase. And what happens in Alzheimer's disease is that you lose cholinergic innervation. And in order to restore cholinergic transmission, drugs inhibit acetylcholinesterase, and that increases acetylcholine levels and restores cholinergic transmission. These cholinesterase inhibitors are well known to you, donepezil and the like, and the problem with them is that they upregulate cholinergic transmission and cholinergic activity in a whole body manner, in a way that results in cholinergic adverse responses, which are commonly described as sludge. And so that limits the clinical efficacy of cholinesterase inhibitors and is a driver for the desire of looking for new ways of treating Alzheimer's disease, and certainly memory loss. Able to use young animals, and so we're not confounded by old animals. We inoculate those animals with a prion-infected brain homogenate when they're 3 weeks of age. And by 7 weeks post-inoculation, we have synaptic number loss. By 8 weeks, we have a deposition of misfolded protein. We have gliosis, we have spongiosis, and the disease is progressing. By 9 weeks, we have synaptic protein loss, and by 10 weeks, we're losing hippocampal neurons. Very importantly, we have a deficit, a loss of cholinergic innervation into the hippocampus, and that results in a cholinergic base deficit in learning and memory, which can be recovered in our hands with administration of donepezil, cholinesterase inhibitor. And finally, these animals go on to have terminal neurodegenerative disease, which we identify with clinical symptoms. But this is the volcano blood. These are the proteins that have been changed in the context of prions. Now, comparing the protein changes compared with control vehicle and prion infected vehicle. And most of the proteins, we've got about 6,000 proteins here in this volcano blot. Most of them do not significantly change, but around about 8 to 10% of the proteins do change. Most of them that do change are upregulated, with some that are downregulated. And these proteins are proteins which have excited us. They are ones that are associated with neurodegenerative disease in humans, particularly Alzheimer's disease. ApoD appearing as the biggest change, ApoE down here, other markers of neurodegeneration, transglutaminase here, these serpines, the inhibitors of proteases, and S100 proteins, the calcium binding proteins, the so-called alarmins, which are involved in neuroinflammation. Others that go up are the complement system are seen to increase, which again associated with human neurodegenerative disease. Markers of neuroinflammation go up, GFAP, vimentin, galactin, clusterin, all increasing in abundance in prion-infected animals. So that's what's happening in prion-infected animals. What happens in prion-infected animals that are treated with VU846? Well, we see a dramatic decrease in the number of proteins that change in prion disease when the animals are chronically treated with 846. And so we go down from around 600 proteins that we saw in prion infected to around 250 proteins, which are changed if we give the animal 846. And those proteins that do change, here we go, ApoD, that's the position we saw in prion-infected animals, but prion-infected animals treated with 846 see much reduced levels of ApoD. Similarly, transglutaminase, that's where it appears. It's now insignificantly changed if you treat the animals with 846. GFAP is dramatically reduced, a marker of astrocyte activation, as are other markers of neuroinflammation decreased in animals treated with 846. The complement system upregulated in prion disease and less upregulated in 846. This is what I'd like to finish with. I want to touch on our thoughts and just round all this up in terms of disease progression. So this is Alzheimer's disease progression on a timeline coming from mild cognitive impairment to severe clinical symptoms. What our studies are indicating is that we require, we would suggest a positive allosteric modulator at the beginning of disease, a positive allosteric modulator which has at its heart high levels of cooperativity, but low levels of intrinsic activity. This, we believe, would restore learning and memory because there's enough acetylcholine around to give you cooperativity to restore learning and memory. But importantly, would have significantly reduced adverse responses compared to orthosteric ligands, and provide neuroprotection in the way I've just described for prion diseased animals. As disease progresses, acetylcholine levels will reduce, which means that cooperativity will be less effective because you simply don't have enough acetylcholine to give you sufficient cooperativity to rescue responses. So you might have to dial in some intrinsic activity into your positive allosteric modulator. And BQCA is one of those muscarinic M1 selective positive allosteric modulators with high levels of cooperativity and high levels of intrinsic activity. And finally, at the end of disease, you will have virtually no acetylcholine or very little acetylcholine there for cooperativity. So positive allosteric modulators will not be effective, in which case you would need an orthosteric ligand such as xanomeline. There's no cooperativity, but there's high levels of intrinsic activity, and you would have the downside of potentially off-target sludge-like symptoms.